Yeah, algebra. This is the second half of our lesson 1.1, operations on real numbers. By operations, we mean addition, subtraction, multiplication, and division. We're just going to focus on the kind of four fundamental math operations. Let's get into it. All right, so this example is in your book. Jim is playing a math game where he needs to put a set of 3 cards in numerical order. I think we're mean from smallest to biggest. His cards, what a weird game, show 40 over 11, the square root of 324 over 36, and the square root of 10. Order the cards from least to greatest. All right, there we go. So the first step they do is find the decimal equivalent for each number. There's some big words here. Decimal just means they want it a decimal form. They don't want the fractions. Equivalent means it's equal to. So first they take 40 and they divide it by 11 in a calculator, and it's going to spit out 3.63 repeating. Then they do the square root of 324 over 36. That simplifies to 18 over 6, which reduces to 3. So these first two are rational numbers, okay? This third one, the square root of 10, is not a rational number. If you put that in your calculator, you're going to get 3.2 blah, 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 and a lot of other numbers. Okay, so they rounded to 3.2. That's why this squiggle equal sign is here. It means the square root of 10 is about 3.2. And so when we're ordering it from smallest to biggest, 3 is the smallest number. And so that's why it goes there on this number line. 3.2 is the next size, and that's why it's here. And the last number is 3.63, okay, repeating. So when you're unsure, please, by all means, use a calculator to find out what these numbers are. But understand that this is an irrational number. It cannot be written as a fraction. And these two, this starts as a fraction, so it is rational. And this, while it looks like an irrational number, can be simplified, and we see that it is indeed a rational number. It can be written as a fraction. So how do we know when numbers end up being rational? Well, this is on page 6 of your book. And the question is the sum, meaning we're going to do addition, of two rational numbers always rational? And here's 3 examples, okay? And they explain here very clearly that you cannot try every pair of rational numbers when you're adding, like these 2 pair here equal 5/6. Because I can come up with an infinite amount of combinations. So how can we know it's true for all rational numbers? Well, what I want you to do, I know this is kind of small, but pause the video and go find this example on page 6 in your book. What they do is they replace all the numbers with variables, meaning they replace the numbers with letters. They use A, B, C, D, and I think they also use E. Okay, so go ahead and pause now and go take a look. And welcome back. Continued on page 6, they ask this question here. Is the product, which means multiplication, of 2 rational numbers always a rational number? And here they kind of cut to the chase. So they use the same strategy they did above it, and they replace numbers, and they just use variables here. So I have letters. So when we do multiplication of fractions, we multiply straight across. And this is going to be a times c, which is, this is another way to write a times c, and b times d, which is here. Okay. And they're also saying that this part does not equal 0. All right, so they have ac over bd. This is just another way of writing a fraction. Maybe it's 12 over, 16. Okay. This cannot be an irrational number because I already wrote it as a fraction. So therefore, every single time I multiply 2 rational numbers, right? Here's my first one, here's my second one. I'm always going to get some other number that is also a fraction, also rational. So now let's summarize, okay? The sum of 2 rational numbers is always rational. I want to be clear here. The word always in mathematics is very powerful. That means there is no exception. Now, the product, which means multiplying, of 2 rational numbers is always rational. Again, we see the word always very powerful. In math, that means there are no exceptions, okay? And then here's some number examples, and then they use variables to prove that it is indeed true. Pardon me. And then they have the other statements here. So what do you get if you add a rational number and an irrational number? Well, they're saying that number is always irrational. And here they show one example. We have an irrational number, the square root of 3, and a rational number. When I add them together, I have a number that cannot be written neatly as a fraction, which means it is an irrational number. Okay, and if you remember from our first video, this is the symbol for the irrational number set. And the same thing is true when we multiply product. They take that same irrational number and they multiply it times the rational number, a fraction, and you get a number that cannot be written as an integer divided by an integer, which means this is also an irrational number. And then here's using variables to prove that that is the case. There wasn't much quote-unquote math to this lesson. We won't start solving equations till later. So your homework for now is on page 9. It's number 11, 13, 16 through 33, all of these. And then 39 has multiple parts. I'll go ahead and complete that. All right, if you have any questions, you know where to find me. This stuff is kind of big picture, and we'll get into solving equations pretty soon. Thank you very much for your time. Take care.